Welcome to today's paper reading. Today's paper is titled, Large Language Model-Based Agents for Software Engineering, a Survey. This paper was published on the AR14 preprint by Junwei Liu and colleagues from Fudan University. The recent advancements in large language models, LLMs, have led to the emergence of a new paradigm in AI agents, specifically LLM-based agents. These agents significantly enhance the versatility and expertise of standalone LLMs by enabling them to perceive and utilize external resources and tools. To date, LLM-based agents have demonstrated remarkable effectiveness in software engineering, SE. The collaboration between multiple agents and human interaction holds promise for addressing complex real-world SE problems. In this work, a comprehensive and systematic survey on LLM-based agents for SE is presented. The survey includes 106 papers categorized from both SE and agent perspectives. Additionally, it discusses the open challenges and future directions in this critical domain. The introduction of this paper focuses on the application of large language models, LLMs, in software engineering, SE. LLMs have shown significant potential in various SE tasks, such as program generation and software testing. The paper also introduces the concept of AI agents, which are autonomous entities capable of perceiving and acting on their environments. Specifically, the paper discusses LLM-based agents, which use LLMs as central controllers to handle complex tasks. The survey conducted by the authors analyzes 106 papers, focusing on both the SE and agent perspectives, and outlines future research directions in this domain. This section introduces the fundamental components of LLM-based agents, including planning, memory, and perception. The planning component breaks down complex tasks into manageable subtasks. Memory records historical data to enhance task performance. Perception allows agents to process multimodal inputs. Advanced systems include multi-agent collaborations and human-agent coordination, which enhance task complexity and human preference alignment. Related surveys highlight the uniqueness of this survey, focusing on LLM-based agents in software engineering, distinguishing it from general domain and other software engineering-focused surveys. Figure 1 provides an overview of the structure of this survey on LLM-based agents for software engineering. It categorizes the content into SE perspectives, which include various software development and maintenance tasks such as requirements engineering, code generation, static code checking, testing, debugging, and end-to-end software development and maintenance. The agent perspective section focuses on the design of LLM-based agents, covering aspects like agent framework, planning, memory, perception, action, multi-agent systems, collaboration mechanisms, and human-agent collaboration. Lastly, the figure highlights the section on potential research opportunities in this domain. Figure 2 illustrates the basic framework of LLM-based agents, which are composed of 4 key components: planning, memory, perception, and action. The planning component decomposes complex tasks into subtasks, while the memory component records historical data to enhance task effectiveness. The perception component receives environmental information, and the action component interacts with the environment using external tools to extend LLM capabilities. The survey methodology section defines the scope of the survey, focusing on papers that apply LLM-based agents to software engineering, SE, tasks. The inclusion criteria include papers proposing techniques or evaluating LLM-based agents on SE tasks, while exclusion criteria cover papers not involving SE tasks or lacking iterative interaction with the environment. The paper collection process involves keyword searching on DBLP and snowballing to ensure comprehensive coverage. After manual inspection, 67 relevant papers were identified, with an additional 39 papers found through snowballing, totaling 106 papers. The statistics show a continuous increase in research interest in this field, with papers published across diverse venues, including AR14. In this section, we explore the organization of collected papers from the perspective of different SE tasks. LLM-based agents are designed not only to tackle individual SE tasks but also to support end-to-end software development and maintenance processes involving multiple SE activities. From the collected papers, we observe LLM-based agents designed for end-to-end software development and maintenance. These agents can generate complete programs based on requirements by performing multiple SE tasks such as requirements engineering, design, code generation, and code quality assurance. The majority of LLM-based agents focus on individual-level SE tasks, especially for code generation and code quality assurance, while a portion of agents are designed for end-to-end software development or maintenance tasks, indicating the promise of LLM-based agents in tackling more complex real-world SE tasks. Figure 3 illustrates the cumulative number of papers published over time, up to July 10, 2024. The data shows a continuous increase in research interest in the field, emphasizing the importance and relevance of the survey. This trend underscores the growing necessity for comprehensive surveys to keep pace with the expanding body of literature. Figure 4 illustrates the distribution of publication venues for the papers, highlighting the diversity of research communities such as software engineering, artificial intelligence, and human-computer interaction. Notably, the majority of papers are published on AR14 and have not yet undergone peer review, reflecting the field's emerging status and rapid development. Figure 5 illustrates the distribution of LLM-based agents across various software engineering (SE) tasks, highlighting their involvement in both individual tasks and end-to-end processes. The majority of agents are concentrated on specific SE activities, particularly code generation and quality assurance. Additionally, some agents are designed to handle end-to-end software development and maintenance, showcasing the potential of LLM-based agents in managing complex SE tasks. The numbers in brackets indicate the count of collected papers for each category, emphasizing the research focus on individual-level tasks. Figure 6 illustrates the pipeline of LLM-based agents designed for requirements engineering (RE). It highlights two main types of agents, those for individual RE phases and those for multiple RE phases. Elicitation is a multi-agent framework for the requirement elicitation phase, aiming to uncover hidden needs while reducing costs. SpecGen is a system designed for generating requirement specifications, which outperforms state-of-the-art approaches. Additionally, some agents, like those by Aurora et al., address multiple RE phases, demonstrating the versatility of LLM-based agents in RE. Figure 7 illustrates the pipeline of LLM-based agents for code generation. The process begins with the chain of thought (COT) strategy, which breaks down the code generation task into manageable subtasks, enhancing generation correctness. Dynamic planning strategies are employed where the next step is determined by observing the current action, such as in code plan, which adapts its plan based on detected code snippets. Finally, iterative refinement is crucial, where agents refine previously generated code based on feedback from various sources, including model, tool, human, and hybrid feedback. Figure 8 illustrates the pipeline of LLM-based agents used for static bug detection. This pipeline emphasizes multi-agent collaboration, such as the approach proposed by Mao et al., which involves different LLMs representing testers and developers. Additionally, the GTLENS framework is highlighted as a two-stage method with auditor agents generating potential vulnerabilities and a critic agent scoring them. The Intelligent Code Analysis Agent (ICAA) concept is also introduced, integrating AI models with traditional static analysis tools for enhanced functionality. Figure 9 illustrates the pipeline of LLM-based agents for unit testing. The process involves iterative refinement to fix compilation and execution errors. TestPilot generates tests by constructing detailed prompts, including function signatures and implementation details. Chatista leverages LLMs to understand method intentions and generate corresponding unit tests, refining them based on feedback. Figure 10 illustrates the pipeline of LLM-based agents for fault localization. It highlights the multi-agent synergy in AgentFL, where multiple specialized agents collaborate to streamline project-level fault localization. RCAgent employs a controller agent overseeing a thought-action observation cycle with expert agents for specialized tasks. Autofl enhances standalone LLMs with tool invocation to explore repositories effectively. Figure 11 illustrates the common pipeline of LLM-based agents for program repair. These agents, such as Chat Repair, Cigar, Repair Agent, AutoSD, ActFix, and Flaky Doctor, iteratively refine patches based on environmental feedback. They leverage tools to compile and execute generated patches, using the feedback to generate new patches. RepairAgent exemplifies a more flexible approach by allowing the LLM to decide when and which tools to invoke, enhancing the iterative refinement process. Figure 12 illustrates the process models adopted by LLM-based agents for end-to-end software development. The majority of these agents follow the classic waterfall process model, which is linear and sequential, dividing the project into distinct phases. Some agents extend this model by including iterations in specific phases to ensure high-quality content generation. Additionally, some works explore the potential of LLM-based agents with agile development models, such as test-driven development, TDD, and Scrum. These models prioritize writing tests before coding and break down software development into iterative sprints. Furthermore, the role specialization in multi-agent systems is discussed, where different roles are assigned to tackle specialized subtasks and collaborate throughout the software development life cycle. Figure 13 illustrates the pipeline of existing LLM-based agent systems for end-to-end software maintenance. The pipeline consists of three main phases: issue localization, patch generation, and patch verification. Some agents include additional phases such as pre-processing, issue reproduction, task decomposition, and patch ranking. Various strategies are employed in these phases, including retrieval-based, navigation-based, spectrum-based, and simulation-based localization. This pipeline aims to automate the process of maintaining software systems by diagnosing and fixing reported issues. Figure 14 illustrates the evolution of benchmarks in software maintenance. SWE Bench, the first end-to-end software maintenance benchmark, includes 2,294 real-world GitHub issues from 12 popular Python repositories. SWE Bench Lite is a subset that eliminates tasks requiring complex edits or containing images and hyperlinks. SWE Bench Verified further refines the benchmark by removing cases with unspecified descriptions or insufficient tests, ensuring a more accurate evaluation of LLM-based agents. The analysis from the agent perspective is structured around the components of agent frameworks, the dynamics of multi-agent systems, and the integration of human-agent collaboration. In the agent framework, we focus on planning, memory, and perception components. Planning involves meticulous task sequencing and strategic scheduling of agents. Memory is crucial for storing historical data to sustain coherent reasoning. Perception enables agents to interpret textual and visual inputs. Multi-agent systems are characterized by specialized agent roles and various collaboration mechanisms, such as layered, circular, tree-like, and star-like structures. Human-agent collaboration is incorporated to refine tasks in planning, requirements, development, and evaluation phases. Key components of agent systems include diverse planning strategies, memory designs, and action components that leverage external tools. Figure 15 categorizes planning strategies and LLM-based agents for software engineering. It highlights the differences between single-planner and multi-planner approaches, single-turn and multi-turn interactions, and single-path versus multi-path planning. This taxonomy helps in understanding the diverse methods employed by these agents to manage complex software development and maintenance tasks. Figure 16 categorizes the memory design in LLM-based agents for software engineering, SE, into four main perspectives: memory duration, ownership, format, and operations. It highlights the distinction between short-term and long-term memory, the types of memory ownership, specific versus shared, and the various formats used for storing data, including natural languages, programming languages, structured messages, key-value pairs, embeddings, and trees. This taxonomy aids in understanding how different memory mechanisms support the complex tasks of SE, such as iterative revisions and collaborative code generation. Figure 17 categorizes the action components used by LLM-based agents in software engineering, SE. These components include searching tools for retrieving information, file operation tools for managing files, and GUI operation tools for interacting with software GUIs. The figure highlights the diversity of tools employed to extend the capabilities of these agents beyond basic language model interactions. Figure 18 presents a taxonomy of agent roles within LLM-based multi-agent systems for software engineering, SE. These roles are categorized into several key groups. Manager roles, which include CEO, CTO, commander, and controller, are responsible for decision-making, planning, and overseeing team coordination. Developer roles, such as programmer, coder, and software developer, are crucial for code generation and refinement. Software quality assurance roles, including code reviewer, tester, and debugger, focus on ensuring software quality through various inspection and testing activities. This taxonomy highlights the specialized roles that contribute to the complexity and effectiveness of multi-agent systems in SE. Figure 19 illustrates the various collaboration mechanisms used in multi-agent systems for software engineering tasks. The layered structure is hierarchical, where tasks are decomposed into substages and assigned to specific agents. Agents collaborate sequentially, passing intermediate results between stages. The circular structure involves multi-turn dialogues and feedback mechanisms for iterative refinement of outputs. The tree-like structure sees agents in the same layer focusing on their own tasks without direct cooperation, often leading to parallel execution. These structures highlight different approaches to enhancing the effectiveness and efficiency of multi-agent systems. Figure 20 illustrates the integration of human participation in various phases of software engineering, SE, to enhance agent performance. The phases include planning, where users can modify auto-generated workflows, requirements, where dialogue-based interactions refine initial task descriptions, development, where human guidance strategizes solutions, and evaluation, where human intervention ensures outputs align with user intentions. This collaboration aims to better align agent systems with human preferences and expertise, addressing bottlenecks in software development. The research opportunities in LLM-based agents for software engineering, SE, are vast. Firstly, developing comprehensive evaluation frameworks is crucial. This includes designing more diverse metrics and constructing higher quality, more realistic benchmarks to provide a fine-grained analysis of agent performance. Secondly, enhancing human-agent collaboration is essential. This involves extending human involvement throughout the software development lifecycle and creating effective interaction mechanisms and user-friendly interfaces. Lastly, exploring diverse perception modalities can significantly enhance the flexibility and accessibility of agents, allowing for more natural and efficient interactions. In this paper, the authors have conducted a comprehensive survey of 106 papers focusing on LLM-based agents in software engineering, SE. The analysis was approached from both the SE and agent perspectives. From the SE perspective, the application of LLM-based agents across various software development and maintenance activities was examined. From the agent perspective, the design of components within these agents was the main focus. Additionally, the paper discusses the current open challenges and suggests future directions for research in this critical domain. Thank you for watching.